All right. This lesson has to do with polynomials, power functions, end behavior, symmetry, things like that. So let's start together. So what is a power function? And so a power function is any function in this form, which is y equals a times x to the n, and n is an integer greater than 0. Or I should say greater than, is an integer greater than or equal to 0. So power function is also a type of monomial, and the word monomial means one term, and you can see there's only one term there. So this is draw a sketch of each of the following monomial. So a constant, we're just going to let C be a constant. What does it look like? It's just a horizontal line wherever C might be. Linear, it's going to be a slanted line. Quadratic, that has an exponent 2, it's going to look like a U. Cubic, that means the exponent 3. So starting at the origin, one end curves up and the other end curves down. Quartic, that's a fancy word for the exponent 4. It actually looks the same in some degree as a quadratic. They have the same basic shape and end behavior. When it's a higher exponent, it's going to look a little skinnier. Quintic, again a very fancy name for the exponent 5. And again, one is going to curve up and the other end is going to curve down. And because of the exponent 5, it's going to look a little skinnier than the cubic, but it has the same basic end behavior and end curve. Now, if the function has an even power, so an even exponent to the power function, that means both ends will either go up or down. Let's look at that. So, well, let's first talk about the symmetry of it. So if it's an even power, then it is symmetric, which means it reflects over the y-axis. We can call this an even function. If the function has an odd power, it is considered to be symmetric around the origin. We call that an odd function. So one of the things that the power function, sometimes we're going to call it the power term, what it gives us is the end behavior of it. Now, there are two behaviors here, two ends. One's called the right end, and the other's called the left end. So, if I look at the right end behavior, I want you to notice that the right end is going up, and a fancy way for saying it's going up forever is in math says it goes all the way to infinity and beyond. The left end, well, when it's even, you can tell the left end is approaching, also going up. And it's also going to infinity. There are more fancy ways we're going to write this as we get closer to calculus. But right now, I want you to focus on that an even one, right? Means the left and right end are both going up. And if they're going up, that means they're going to infinity. How about if you have an even exponent, but a, the coefficient in front, is not positive, but it's negative? What does that negative do to the end behavior? So this time, if you look at the picture, the right end is actually not going up, but going down. And in math, if it goes down forever, it goes to negative infinity. The left end is doing the same thing. So if you look at both ends and what direction they're both going down, and in math that means they're approaching negative infinity. Look at the next example. What happens if you have an odd exponent and notice it's positive in front? What happens to the end? Well, they go in opposite directions. So the right end goes up, which means it's approaching infinity. But if you look at the left end, you can see it's going in the opposite direction. So the left end is going down, which means it's approaching negative infinity. What happens when you put a negative with an odd exponent? Well, it then reflects and it changes direction. So now instead of the right end going up, now where's the right end going? So now we can see the right end. Oh, it's down here. So instead of going up, what's happening to the right end? It got reflected down. So now the right end is going down, which means the right end is going to negative infinity. The left end, what direction it's going? It's going up. So it's going to infinity. All right, turn the page. We're going to practice that and sketch it. So for these power terms, the domain and range are going to be all real numbers. There are no breaks, nothing that makes it undefined in terms of the range. Or the domain, I should say. The range, however, if it's an even, will actually have a bottom or a top point. So we'll come back to that. The x and y intercept for this is going to be 0. Is it increasing or decreasing and where? And we'll talk about that. The picture of this, when it has an even exponent with a positive number in front, it's going to be parabolic in nature. So it's going to be going up in both directions. I'll plot another point. So if I plug in 1, the answer is 3. And if I plug in negative 1, the answer is 3. So I know the sense of it and what the picture is. There's the picture of it. And notice both ends go up. Why? Because we have an even exponent and a positive number in front. If I said, where is this increasing? Well, increasing means from left to right, it's going up. So actually, if I look left to right, the first part is going down. So if I said from negative infinity to 0, it's decreasing. And then when does it change direction? At 0. And from 0 to infinity, it's increasing. So one part's decreasing, it changes direction, and then increasing. Symmetry. Does this have symmetry over any axes? And you can see it has symmetry over the y-axis. We call this an even function. Are there any discontinuities? Means, are there any breaks or holes or anything, or is it just a continuous function? So there's no discontinuities. What do you think the end behavior is? What direction is the right end and the left end? So we're just going to go pure math here. So the right end's going to infinity, and the left end's approaching infinity. Done. All right, try the next one and see if you can see the end behavior of these power functions, and if you can graph it. So we have negative 2x to the fifth. Again, it's going to be all reals for the domain. The x and the y-intercept is going to be 0. And then, how do I know how to graph this? Well, what does an odd exponent do? What direction? Well, it normally goes up to the right and down to the left. But the second part is, there's a negative in front. And that negative in front changes the direction that would normally go. So if I plug in 1, I get the answer negative 2. But if I plug in negative 1, I get the answer positive 2. And so you can see the direction that this is going. If I said, where is it increasing? Well, if I look left to right, it's not increasing at all, nowhere. And if I look left to right, it is decreasing all the way through the function. Left to right, it's going down. Is there any symmetry here? And because it's an odd exponent, there's symmetry around the origin. That's why we call it an odd function. There are no discontinuities, meaning there's nothing. It's continuous all the way through, no breaks of any sort. And what's the end behavior? So the right end is approaching negative infinity, while the left end approaches infinity. Number 3. At any time you want to try this yourself, you can. Then press pause and come back. So, again, it's all reals. Oh, I didn't actually say the range for this. So the y does not have a top or a bottom point. It goes from the top all the way down. So that means the range is also all reals. So when we have an odd exponent for the power function, it's all reals for both. If you have an even exponent, it's all reals here, and then I didn't even do the range here. Well, what's the bottom value right here? So the bottom value is 0, and it goes to infinity. All right, let's try number 3. So the domain is all reals. Let's see if we can graph this. So again, our intercepts are at 0, 0. What direction is this going? Well, if I see an even exponent, it either means both ends are going up forever or both ends are going down forever. The other indicator is the negative. So with a negative and an even exponent, both ends are going down forever. I would like another point if it fit on my graph. I'm going to count. 1 gives me negative a half, which is fine, but 2 to the 4 is 16, and half of 16 is 8. So negative 8. 1, 2, 3, 4, 5, 6, 7, 8. It does fit right here at the bottom. If I put in the answer 1, I get, well, that's, that was 2, wasn't it? So if I plugged in 2, I get that answer. Let's erase that one. 1 gives me negative a half. Negative 1, it reflects over here. Let's get them correct. So not these right here. So 2 gave me the answer negative 8, and negative 2 gave me the same answer. There it is. Sketch the best I can. The range, notice we have a top, so we go bottom to top. So the bottom is negative infinity and it goes to the top, which is 0. Increasing, well, we start increasing. It goes from negative infinity to 0. So it starts increasing. At what x value does it change and then decrease? So it decreases from 0 to infinity. We have symmetry on the y-axis. There's no discontinuities. The end behavior, where's the right end approaching? Negative infinity. Where's the left end approaching? Also negative infinity. So we can describe both ends. All right, let's talk more specifically about polynomials. So there's a not very easy way to look at what a polynomial looks like. But one thing I want you to remember is that a polynomial is determined by the exponents that you see on the variable. And if the exponents are positive integers, no fractions, no negative exponents, no variables in the denominator, just positive integer exponents on the variable, then it is a polynomial. So polynomials in terms of shape and continuity. So polynomials are smooth curves with no breaks, holes, or corners. The graph is continuous, so that it goes forever left to right. Degree. What does the word degree mean when we talk about a polynomial? So degree is the greatest exponent. So if you look at a polynomial and you can tell me the greatest exponent that you see on the variable, that exponent is called the degree. So here are some examples of polynomials. So the first one, I don't see a variable at all. So when you don't see a variable at all, the exponent you don't see on x is actually 0. And we call that a constant. It never changes. No matter what number you put in for x, the answer is always 2. The next one, you should recognize this, mx plus b. The degree, again, I don't see the exponent, but I see x. So that means the invisible exponent you don't see is 1. We call this a linear, a line. Look at the next one. What's the greatest exponent you see on the variable? That's called quadratic when the greatest exponent is 2. Look at the next one. What's the greatest exponent you see? 3. We call that cubic. Look at the next one. Notice I'm not looking at the large numbers in front, the coefficients. I'm looking at the exponents. So here, the exponent, it's 4. We can call this a quartic if we want to. The next one, the greatest exponent you see is 5. Sometimes it's called a quintic. Usually, when something has a degree bigger than 3, we just call it a higher order polynomial. And that we don't use these names quartic or quintic, though it's fun to know that they could be classified that way. But it is expected that you know a constant, a linear, a quadratic, and a cubic. So these first 4 should be good vocabulary for you, and then after that you can just call it a polynomial. So the power and coefficient of the leading term determine the end behavior of the function. So we already worked on power functions. If I said, what's the end behavior here? And we actually filled this one out. Did we do this one just like a moment ago, right? So we already did this one. So when it's positive with an even exponent, you know the right end and left end are approaching infinity. When you have a negative with an even exponent, it means that both ends are going to negative infinity. So it's important to know that an even exponent means both ends are going in the same direction. When you have an odd exponent, it means they go in opposite directions. So when it's an odd exponent with a positive number in front, the right end is going up while the left end is going down. So notice when it's positive in front, the coefficient, the right end is always going up. When it's negative in front, you're going to see that the right end's always going down. And then the other end goes in the opposite direction. So you can tell the right end behavior in terms of whether it's positive or negative for any of them. And then if it's an even exponent, that means the other end is going to join it, or it's going to go in the opposite direction if it's an odd exponent. Using the leading term, can you tell me the end behavior of each polynomial? So for number 1, to understand that, I need to understand the power term. And I'm going to use that. We can call it a power function when we write it as a function, y equals. But if I don't have that, if it's just the term, and that's really all I need, I'm going to call it a power term. So it's the term that contains the biggest exponent. So the biggest exponent is 4, and the full term is what's in front of it. So the full power term is negative x to the 4th, and then that tells me the end behavior of the function. So in this case, what two things am I looking at? Even exponent with a negative in front, so the right end and left end. So right away, negative means the right end is going down. Even exponent means the other end is going to join it. So power term, I'm just going to say PT. Which term has the biggest exponent attached to it? So it's negative 2x to the 5th. That tells me the end behavior. So what do I notice? It's negative in front, that means the right end goes down. Has an odd exponent, that means the other end goes in the opposite direction. Again, when you want to practice it, press pause. So the term with the biggest exponent, 6x squared, the right end is going up because it's positive. The left end will join it because there's an even exponent. Again, the power term is 4x to the 7th. That means the right end, it's positive, is going up. The left end, because it's an odd exponent, goes in the opposite direction. The power term is 1/2 x cubed. I'm not worried about the fraction, just the sign in front. So it's positive 1/2. That means the right end is going up. The odd exponent means it goes in the opposite direction. Last one, power term. Negative 3x to the 8th. What does that tell me about the ends? So negative means the right end goes down. Even exponent means the left end joins it. It says describe both the power function and coefficient of the leading term of what's given. So what do we know about this? Well, we know what direction. Are they going in the same direction or opposite direction? And because they're going in opposite directions, you must know that there must be an odd degree to the power term. That makes it go in the other way. And what do you think about the coefficient? Where's the right end going? So there must be a negative coefficient. That's the number in front. And why is it negative? Because the right end is going down. Try this one. Look at the two ends. What direction are they going? And what does that tell me? So if they're both going in the same direction, that means there must be an even degree, an even exponent on the power term. And the second thing is the right end is going up. So if the right end is going up and the left end, there must be a positive coefficient for that to take place. All right, let's do some vocabulary here. This is the point at which a polynomial function switches direction. So if the turning point is higher than any nearby point, it's called a, and there's two words that are used here. So it could be called a relative minimum or maximum, it's higher. Sometimes it's called a local maximum. So in its local area, it's the highest point. If the turning point is lower than any nearby point, it's called the relative minimum. And again, sometimes instead of the word relative, we use the word local, and it means the same thing. The maximum and minimum values are called, and then here's a fancy word, extrema or extrema. So if you say that word, you mean the extremes of the function, the tops and the bottoms. So turning points define where the function is increasing or decreasing. So if a function turns, that means instead of increasing, it's decreasing, or vice versa. So can you find the turning points of this function? And it says graph the function using a calculator. It talks about using a calculator menu. For this course, I'm going to allow us together to work on Desmos to be able to feel good about that. On a test or quiz, I will give you the turning point. And then when you get to calculus, we'll learn how to do it by hand and learn with our calculus calculator how to do it. So what I'd like you to do is go to Desmos. I'd like you to have Desmos, D-E-S-M-O-S, Desmos. I'd love for you to download that on your phone. It's the best calculator there is and free. It's like a green symbol to it. Then it's right there for you on your phone or on your Chromebook. Go to desmos.com. I want you to type it in. If you don't see all that you need, that means you got to press the minus sign so that you zoom out. And then after you type it in the first box, you'll see where it turns. And on Desmos, every turning point is like a little gray point you can click on, and then you see it right away. So you practice this. I wish I was handier with video where I could have like a split screen so you could see Desmos in action, but I can't. I don't. One day. Who knows? But I need you to see that there's a maximum at -4 and 47 when you click on it. And I need you to find where the minimum is. Now the minimum's a decimal, so I'm going to round it to 0.67 and -3.81. If you don't know how to do this with your phone, with the Desmos app, or on your Chromebook, I want to help you and ask me. All right, increasing intervals. So these tell you where it's increasing and decreasing. So when we have a maximum, that means that up to -4 from left to right, it must be increasing, and then after -4, it must be decreasing. So up to -4, it's increasing. Afterwards, it is decreasing. And then after it decreases, it then increases again all the way through. All right, let's work on knowing how to graph polynomials and let our calculator support us a little bit. So when I'm graphing this, classifying, could you name it? This is a quadratic. And how do I know that? Because of the power term And even though it doesn't ask for the power term, I'm going to make sure you say power term. So what's the power term? It is x squared. So I know what that shape looks like, the end behavior. When graphing quadratic and it's not in factor form, you're allowed to graph this and help it with your calculator. I'll give you some hint about this. Is if you didn't have a calculator and it's a quadratic, there's a formula that helps us find that turning point, and it's negative b over 2a. That's not going to help us as we move on here, but for this one it will. So it's okay for these if you use a calculator and support it with your calculator. So that means Desmos to type it in, but I'm just showing you this by hand, and we'll come back to this later in the course. But b, it goes a, b, c. So b is 2, but it's negative because the formula is negative. And a, you don't see a number in front of x squared, that means it's 1. So when you simplify it, this is negative 2 divided by 2, you get negative 1. And then to find the y value of the vertex, you would plug negative 1 back into the equation and then simplify it. And that gives you negative 1 and negative 6. You can then do a table of values if you like. So if I plug in 0, the answer is negative 5, and you can reflect over the axis of symmetry. If I plugged in 1, I get the answer negative 2, and that's enough for me. So there it is. If you use Desmos, you'd see the same picture. Desmos will also give you that turning point if you click on it. All right, what's the domain? It's all reals. What's the range? Well, we have a bottom turning point. So the bottom is the y value there. And we said that's negative 6, and it goes to infinity. Is there any relative minimums? Yep, down there. And that relative minimum's at negative 1, negative 6. Is there any maximums? No. There's no turning points above, just one lower. Where's it increasing? So from this x value, which is negative 1. So from negative 1 to infinity, it is increasing. Where is it decreasing, left to right? So from negative infinity to negative 1, it is decreasing, and then at negative 1, it changes to increasing. What's the end behavior? Where's the right end and the left end? So the right end and the left end both are approaching infinity. It's going up on both sides. All right, number 2. Here's one I want you to type in Desmos so that we can get a sense of it. We'll learn how to do this more later in this unit to do it without Desmos. But right now I want you to go to Desmos, and in particular what I want you to find are where the turning points are. So type this into Desmos, press pause, and then let's see if it's together. So if you see where it turns, it should turn at negative 1 and negative 7. That's a bottom point. It should also turn at negative 1 and positive 1. That's also a turning point. So I'm going to put those on my graph. Oh, this is wrong. So negative 1 and negative 7. The other one was 1 and 5, there we go, is the top turning point. So negative 1 and negative 7, and positive 1 and 5. I know there's a y-intercept at negative 1, because if you plug in 0, the answer is negative 1, so that's nice to know. And then we're going to connect this with a smooth curve. I mean, if you also hit Desmos, you could also see where the intercepts are. You just click where it crosses, so you can have an approximation of it. But what I really want to get a sense of is that you see it's a smooth curve using these points. And we're sketching it to connect it together. Notice the power term is negative 2x cubed. And that means the right end is going down because it's negative in front, and the left end's going up with an odd exponent. Where is this increasing or decreasing? This has to do with the x values of the turning points. So first, this is decreasing. So from negative infinity to negative 1, it is decreasing. Then it increases from negative 1 all the way up to positive 1. And then the last part of the graph, from positive 1 to infinity, it then decreases. Why am I putting it there? From positive 1 to infinity, it then decreases all the way through. All right, number 3. Again, type it into Desmos and find the turning points for me. So as you're doing that, I see that the power term is x to the 4th. So that already tells me the end behavior. The left and right end are both going up because it's positive with an even exponent. Oh, I didn't classify this one way up here. Let's make sure I fill in the whole chart. Because the power term has exponent 3, it's cubic. The domain is all reals, and the range is all reals with that odd exponent. It goes up forever and down forever. All right, now that I filled that out. Here to the 4th, so we can call it a quartic, but it's going to act like a quadratic. The domain is all reals, but there will be either a bottom or top to this quartic with the even exponents. So it's not going up forever and down forever. So where are their relative minimums and maximums? So use Desmos and click. So round the answer, it's a decimal. So there's one very close to negative 1 and negative 1. There's another one that's close, and I'm going to round to about 2 and negative 7, just rounded. There's a top turning point exactly at 0 and 1. So I'm going to put those on my graph. So about negative 1, negative 1, 0 and 1, and 2 and negative 7. Now, the last thing I'm going to connect these points is understanding the end behavior. What direction are both ends going? So I know the right end is going up, and I know the left end is going up. So as I connect these, and you can see the picture on Desmos, understand that the left and the right end go up. So this then becomes the bottom of my range. So the bottom of my range then is about negative 7, and it goes up to infinity from there. Where is it increasing? So it decreases. There's a little increase here. So the x values of these turning points. So at about negative 1 to 0, it's increasing using the x values. Where else is it increasing? Well, down here at this turning point, the x value of that turning point, which is 2, and it goes to infinity. Oh, here, 2 to infinity. So those are the two areas where the graph is increasing, here and then at the very end. Where's the graph going down, left to right? So if I look left to right, where's it going down? So from negative infinity, what's the x value here at this turning point again? It's negative 1. And where else is it decreasing? From 0 to the x value down here, which is positive 1. The y value is negative, but the x value is positive. Or is that 2? That's a 2, isn't it? So from negative infinity to negative 1, and then from 0 to 2, it's here, 2 and negative 7. So the x value is 2 in terms of what's happening. Try it again. Type the next one into Desmos. I'm looking for the turning points. You can also find the intercepts on Desmos, and then we're going to put it on here and be able to write the analysis. So I see the power term is x to the 5th. We can call that a quintic if we want, or just a higher order polynomial. The domain is going to be all reals, and because of the odd exponent, the range is also going to be all reals. So it's going to go up forever and down forever. Now we already know the end behavior because of the power term. So we know the right end is going to go up forever, and the left end is going to go in the opposite direction. It's going to go down forever. So on Desmos, type it in and find the relative minimums and maximums. So at about negative 0.4 and 2.4, we have a minimum. We have another minimum at about 1.5 and 0.10. We have a maximum, a top turning point, at about negative 1.5 and 5.9, which is basically 6. We have another maximum turning point at 0.4 and 3.5 to be able to approximate on our graph. So we're going to do that right now. So let's put those points on. So negative 0.4 and 2.4, 1.5 and 0.10, so just barely below, 0.10, just barely above, I should say. Negative 1.5 and 6, and 0.4 and 3.5. All right, so there are my points. So each one of these points, the graph is going to turn. The end behavior, the right end is going up, and the left end is going down. So I already know what my ends are doing, and then I just curve to connect the points that are in the middle. So this is increasing from negative infinity, and we're going to use the turning points. So this turning point goes from negative infinity to negative 1.5. It's also increasing this little section there, which is a negative 0.4 to 0.4, and it's also increasing all the way on the right side. So that last turning point there, the x value there, is about 1.5 to infinity. Where is it decreasing? So one section where it's decreasing is right here, going down left to right. So that's negative 1.5 about to negative 0.4. Where else is it decreasing? One more section from here to here is decreasing. So the x values there is about 0.4, and it goes down to about 1.5. All right, two more to practice. So number 5, type it into Desmos, you try it, then come back. And then we'll analyze it together. So the power term is x cubed. That's a cubic. The domain would be all reals. And so would the range, because it has an odd exponent. It goes up forever and down forever. The power term is positive with an odd exponent. That means the right end is going to infinity while the left end is going to negative infinity. On Desmos, can you find the minimums and the maximums? So we have a minimum at 2 and negative 2. And we have a maximum at 0 and 2. So we're going to put those on our graph. So as soon as I put those down, I then look at the end behavior. So the left end is going down and the right end is going up. And then I can connect the rest. So it's increasing from negative infinity to the x value there, which is 0. It's also increasing here. The x value there is 2 to infinity. It's decreasing from 0 to 2. Or 0 to, 0 to 2. All right, number 6. Last one practice here. Type it into Desmos. I wonder where the turning points are and then put them down. So I see the power term is negative x to the 4th. So it is considered a quartic, which is like a quadratic. The domain is all reals, but the range is either going to have a bottom or a top. So the right and left end behavior, because the power term is negative, I know the right end is going down. Because of the even exponent, the left end is going to join it. So when you looked in Desmos, we're going to round this. We have no minimums, but we do have a maximum at negative 1.8 about and 6.4. So I'm going to put that on my graph. And that's the only turning point in the whole graph. So I do know that there's a y-intercept at 2, because when I plug in 0, that's a simple one. So I know this is going to go down. If you look on your graph carefully, there's like a little hiccup here as it goes down. Honestly, I care about the end and that it's smooth and continuous. So there is what's called a point of inflection in there, but we're not talking about that now. End behavior, smooth and continuous. How many turning points are there? There's just one. So where's it increasing? So from that turning point going down, where's it increase? So left to right, it starts increasing, and the x value there is negative 1.8. And then from negative 1.8 to infinity, it goes down. Perfect. All right, so here's like a practice document or homework where you get to practice these concepts. So I'm going to do that in a different video and really hope you practice this all first and then go to the video and follow what you need to follow. All right, Mr. G Math, over now.